Hello everyone. Today I'm going to be explaining the combination of resistors in a circuit. So the resistors can be combined in many different ways in a circuit, right? So there is Wheatstone bridge, then you have series, parallel, etc. Right? So basically, when we combine resistors in some orientation, then we have to calculate the equivalent resistance by obeying some laws, right? So this is basically the fundamental crux of what is called combination of resistors. So let us start with the two primary ones, which are series and parallel. So first of all, let's discuss about series. Assume that let's take two resistors for simplifying the case. So let's just take a circuit with a battery, and there are two resistors, one, two, like this, right? So now let's assume that the voltage offered by this battery is V. Now, as you see, this voltage will offer some current, right? So it will produce some current I. And now, when this I passes through this first resistor, right, it's going to leave the first resistor and come out in the same form, right? There's not going to be any decrease in the current, right? So as it passes through this resistance, is the current will still come out with the same value. And again, as it passes through this resistor, it's going to come out with the same value, I. So the main point in series is that the current remains constant throughout, right? There is no current division here, right? Because when it's going from here, it's passing through basically an obstacle, and then when it comes out, and it's again coming out in its true form, right? But let's talk about voltage. What happens to the voltage when it passes through a resistor, right? Now, assume this has a resistor of R1, right? This resistor has resistance R1, and this resistor has resistance R2. Okay, so now, first of all, this total net voltage is V. So the voltage here, right, plus the voltage here should give me this voltage because this is the main, the catalyst for giving out the voltage V, right? So in that case, whatever voltage is produced here will be added to this voltage here, and that will give me the final voltage V. So that means there is some voltage drop at every resistor, right? Because if you see, as current is going through it, some of the force, right, voltage is basically what pushing of the charges, right? Whatever helps the current to pass through, that is what voltage does. So as resistance acts like a friction force, that will also reduce the ability of the battery to push the current with ease, right? So that is why there is some voltage drop, right? This is a very important concept. So that is why assume that the voltage here is V1 and here it's V2. I assume that you know Ohm's law, right? V equals to IR, where V is your potential difference and not potential, right? And I is your current and R is the resistance. So here I will get V equals to V1 plus V2, and this is my equation, right? So now if V equals to V1 plus V2, right? I can say I times the resistance, which I don't know. I have to find this resistance actually. And since the current is constant in series, I can say that the voltage V1 is IR1 plus I R2. Now this I and I will get cancelled with this I because if you take it common, it's going to come out and you will see the cancelling. So R equals R1 plus R2. So in the case of series, you will see that the sum of the net total resistance is actually just the sum of the resistors, right? So if you have R1, R2, R3, R4, so many resistors, then you just add all the values, you will get your equivalent resistance, right? And always remember that the voltage varies, right? Voltage is a variable in the case of series, right? So variable, and your current, right? Because it's whatever is going in is coming out, right? And that is why it's a constant. Now let's actually see what happens in another situation, right? In this case, these two are very, very important, right? The fundamental, you know, detail of the series combination is that the voltage is variable and the current is constant. So now we have another combination which is known as the parallel combination, right? So as the name suggests, the resistors are they're actually in parallel with each other. So I'll show you the demo, how it's connected. So for simplicity, I'll assume that there are three resistors like this: one, two, and three, right? And this is connected with a battery that offers a voltage V. And let resistance be R1, R2, R3, and assume that this voltage offers some current I, which passes through the circuit. Now, this I, when it reaches here, right, it's going to divide across these resistors, right? Because that's the only way it can come back to this voltage, right? The main aim of this current is to complete a path of a circuit. So that means it has to divide here to come out in the form of I again, right? The current should remain the same because your battery is not changing. If I had another battery of V dash, then my current would have changed, right? Because every battery has some sort of strength. Okay, cool. So when it's dividing, assume that current I1 goes through this, current I2 goes through this, and current I3 goes through this. Okay, and now this is plus and minus, right? So since this voltage offers a voltage V, I will assume that at this point my potential is V, potential, not potential difference. And at this point, my potential is zero, right? So then my potential difference is satisfied, which is V volts. So now, since now check in between this point and this point, there is no resistor. That means there is no potential drop, right? So whatever voltage is here will be here too, right? In the case of series, if you actually observe, right, here there will be voltage V itself because there is no resistor. But over here, it will not be 0 volts, right? Because in this case, there is a resistor here, right? So that is why you will see a potential drop. But here, there's nothing, right? There's nothing. So here too, you will have a 0 volt potential. And if you see, everything is connected between these two potentials, right? So everything is having a potential difference of V. And this is the beauty of parallel connections. The potential difference, which is V, is actually remaining the same, but the current is dividing. So in this case, the current is a variable. So it's basically the reverse case of a series combination. So this is a variable. Now, in this case, if you saw, we took the variable and made a equation, right? So in this case too, we'll do that, right? So we have I1, the most logical, right? This is just like how you use water, right? When you pour water into a vessel or three vessels, and then you again pour that whole water into another vessel, which is a big one, you will get the same amount of water which you had initially before pouring, right? It's exactly the same thing. This is actually also named as Kirchhoff's current law, right? KCL, Kirchhoff's current law. You can research on it. Basically, it says that when a current divides at a junction, right, at a point, After division, the place where it again meets, it's again going to pass through the same net current it had before division. So if a current I, if this voltage produces some current I, and it divides at this point, after joining here, it's again going to leave with current I happily. That is what Kirchhoff's current law states, right? So I1 plus I2 plus I3 equals to I, right? And we know that V equals to IR. So I equals to V by R. Agree? Now, I1 is basically V by R1, right? Why am I saying V? Because everything is connected between these 2 points, right? V and 0. Plus V by R2 plus V by R3 equals to V by the net resistance, right? R. So you will see that the voltages are getting cancelled, right? If you take them common, right? I'm doing it directly here. You can take them common and see that you will get the same result. So from this, 1 by R1 plus 1 by R2 plus 1 by R3 is actually equal to 1 by R. So in the case of series, it's just a sum, but in this case, you have to take the reciprocal of each resistance and equate it to the reciprocal of the equivalent resistance, right? So when you get this value, right, in fractions, and that's equal to 1 by R, remember to reciprocate in the last because 1 by R value will be something, but that doesn't give you the net resistance. So remember to find, your main aim is to find out the value of R. So in the last, just remember to reciprocate because that's what people forget often. So now this is the concept of parallel and series. Now let's talk about a concept which is very fundamental in physics. That's Wheatstone bridge, and generally people say it as balanced Wheatstone bridge, right? So there is a case of unbalanced Wheatstone bridge too, but here we'll only be discussing about something called balanced Wheatstone bridge. Okay. So now imagine you have a circuit like this, right? And then, right? And then this, and you have a battery here. Okay. Assume this has some, it's offering some voltage V, and then there's some current I like this. Okay. Let this have some resistance R1. Let this be R2. Let this be R3. Let this be R4. And similarly, let this be R5. So in this case, you will see that after current leaves from here, current will be divided like this. But at this junction, right, it's not very clear what's happening, right? Because you can't see if it's in series or in parallel, right? See, it's going like this, and again it's coming like this, right? So this is a case of Wheatstone bridge, right? So in a Wheatstone bridge is actually pretty simple. If, right, this is only in the case of balanced Wheatstone bridge. If this condition is true, wait 1 second. Let's name this as R3, R4. Yeah. If this is the condition that is satisfied, then you can say that this is a Wheatstone bridge. And then it means that there is no current that passes through OCs also. R5. So you can just remove it. This is the concept. There is no current that passes through R5. This means that you can just see R1 and R3 in series, and R3, R2 and R4 in series, and you can simplify a circuit. This is the concept of Wheatstone junction. And these are some of the combinations I've illustrated for you. Thank you.